Okay, today's January 14th. I'm actually re-recording or recording this meeting presentation because this morning forgot to hit the record button, or at least it didn't take the audio portion of the presentation. So I'm going to try to move through this somewhat quickly, but this is a review of what we went over this morning. With regards to AEG power systems or AEG-PS rectifiers and or power supplies, or sometimes you'll even refer to as battery chargers. So those terms can be used interchangeably. The SPRe and the TPRe rectifiers are the installed rectifiers of choice for Avangrid, for RG&E and NYSEG. The S indicates single-phase units, and T are three-phase rectifiers. So we're going to go over the operation, maintenance, and some basic troubleshooting. We're going to look at here. There we go. The overall operation, the interface, the operating instruction and menu as it relates to monitoring, configuration, and actual setup of the unit, as well as some control functions, maintenance, troubleshooting, batteries, and NERC requirements. So the overall basic operation of any charger, you have, I'll take a step back here and mention that AEG is a European manufacturer of these units. They're based out of Madrid, Spain. So you're going to see some terminology. It'll make sense in context, but it's, again, what we would probably call AC input. They'll refer to as mains. So that's what we're looking at here. They're talking main AC input into the charger. It's rectified DC output going out to the load, and mechanically tied to the load is the battery. So you don't have a transfer switch or anything like that to worry about. It is hardwired. There may be a fuse in the circuit or a disconnect, but there's no transfer switch or anything like that to worry about. It should be mechanically connected to the load in parallel. So in the event that there is a mains or AC power input failure or loss to the charger itself, or the charger fails for any other reason, the load is directly supported by the battery without having to do anything. Once the power is restored and the rectifier charger comes back up online, then it goes back into this condition up top where you have current going out to the load, and then usually a pretty small current going to the battery. Assuming the battery is fully charged, a lot of the batteries in your network are anywhere from 100 to maybe 300, maybe as large as 400 amp per hour. So you could see float currents anywhere from a half of an amp to maybe an amp and a half. But again, that's dependent on amp per hour, size of the battery string, and if you have multiple parallel battery strings. Certainly the more battery, more amp per hour, the more charge current that's going to be required. This slide displays in a lot more detail what's going on with the AC line input. So it's going through a transformer, a bridge. Actually, that's probably something I should mention too. These rectifiers are thyristor or SCR rectifiers. There are some other different technologies out there, switch mode, ferro resonant. But again, for utilities, this is pretty much the industry standard. It's a proven technology. They've been installed hundreds of thousands, I don't know, maybe hundreds of installations. They're workhorses. They're very durable, very, very resilient. Hot environments, dusty environments. Again, just a real solid technology, and that's why you see them deployed as much as you do in utility, gas and mining, oil, chemical. They're just a very popular style of rectifier. Takeaway from this slide would also be this related to AEG rectifiers, and that's the GCAU board. This board is for lack of a better term, the motherboard or the main board to the system. There are other alarm boards and circuitry involved within the system itself, and I'll show you that. But this is really where a lot of monitoring is done, communication interface is done. This serial communication board listed as an option on the drawing. It's installed on, this option is utilized on, I believe, on almost every installation I've come across out in the field. So I know it's used in, and certainly, if not all, a vast majority of the systems that are installed across NICEAG and RG&E. Also, your interface board runs through the GCAU. So it's, again, an integral part to the overall system. So when the battery charger rectifier is operating normally, the output voltage is what we call the float voltage. Certainly dependent on what's required to drive your load, but it's also probably more specifically set to the batteries that are in parallel to the load. So you want to make sure you're not undercharging or overcharging those batteries. Your load has a very wide window, or certainly wider than what a battery would expect to see for a normal operation. So we really kind of, the output is factory set around the battery itself, knowing that it's, you know, going to be comparable to whatever your load requires. So 92 cell systems, because these are NiCad batteries, nickel cadmium batteries, 142 per cell, 92 cells in a string, gives you a nominal of about 130.5 volts. Equalization, boosting, commissioning charge, while not exactly the same things, some people use them interchangeably. That charge rate is usually around 152. Your equalization charge and commissioning charge may be a little bit different from each other. So there's an equalization charge and then a commissioning charge. Sometimes the commissioning charge is still at that voltage, at that high voltage, but for a longer period of time than the equalization. So the takeaway there is the commissioning is usually a more intense charge, whether it's higher voltage or longer duration. In the instance of AEG, I believe it's actually a slightly longer duration. So they do equalize, or they do both have the same high rate charge, but the commissioning just goes for a longer period of time. This is the inside of the rectifier. The resolutions, I apologize for that, diluted a little bit when as I expanded it, but I have some pictures later in the presentation that'll show it much more clearly what's going on. But the key aspect to here, your AC and DC power coming from the bottom. These terminals are very clearly marked as to AC input and DC input, as well as polarity. I will say one thing for AEG versus if you're used to seeing or working on other rectifiers in the field, say like an Exide, a Hindle, C&D Charter systems. AEG are considerably larger. They're very easy to work on, at least user-friendly from the aspect of area inside of the cabinet. Everything is very clearly labeled as far as fuses, boards, disconnects, and switches are capacitors. Everything is very clearly marked on the unit as well. Again, making them service friendly. This is the backside of the interface display that we're going to be talking about here in some greater detail. Here's what it looks like from the outside of the unit, and that display will show you the output information, DC, the voltage, current, and then it also goes through the alarms, and then these three guys down here are really we're going to allow you to interact with the menu of the controller, and left, middle, and right keys, and I'll show you their function here as we go through this. So this is you walking into the station, and just what that previous slide showed that, hey, DC output, 127 volts. There's our 9 amps. Now that's load going to the battery. That's current going to the battery and the load. Again, probably about 1 amp or less of that is going to the battery. Vast majority of that is going out to the load. no alarms present. And I should mention green LED on the left-hand side when everything's great, amber orange LED on the right-hand side when either an alarm is active or an alarm has come in that has been latched. The latching of an alarm is set up at installation. Typically, the alarms that I've seen as they've been set up in the field for NICEAG have been that the alarm clears when the incident clears itself. So it pulls it every so many seconds, and then again, the situation is rectified or cleared or corrected, the alarm goes away. Now it'll be logged in the alarm and time stamped, and we'll go through that. But again, that's that it's probably not a bad way to have your system set up, because of you get latching alarms. People may not necessarily know how to clear it. It could cause some confusion thinking that it's active. Again, that's kind of my preference, but from what I've seen, you don't have latching alarms in the field. Almost everything is real time. So when you walk into, I'll go back here, you're walking into your room and boy, everything looks fine. Yeah, you have your display, no alarms, but you do want to drill down, take a look at some history. You want to take a look at some parameters. You maybe even want to do some command functions. I'm going to show you how to do that with these 3 buttons on the front of it. So you hit any of these 3 buttons. Once you again, you get in that room, any of those buttons you hit, this is going to come up. These X's here will probably say, well, it'll tell you the status of the rectifier. And usually it'll say DC float or charge float. I forget. I have the slide a little further into this, so it'll tell you exactly what that says. But it'll give you the indication. So if you're under load, if you're in a rectifier failure or you're in a float condition, it'll tell you the status of the rectifier. Again, more often than not, it's just going to be in a float condition, just charging the batteries and supplying current and voltage to the load. So you don't need to hit any of those 3 red buttons underneath there, and you have monitoring, configuration, and commands. The nice thing about AEG rectifiers, when you get out in the field, if you want to scroll through the menu, play around with the menu, you're not going to inadvertently impact any operation of the rectifier or on the output of the rectifier. Anything that would potentially cause any issue is password protected. So you come across something, you got to a part of the menu you didn't intend to, a password prompt comes up, you certainly don't want to mess with that. You just hit exit. It'll take you back up to the top level of the menu, start over again. So you're without password protection. And frankly, even there's 2 levels of password protection, and well, we'll hit those. But again, it's with even the user password protection, you're not going to impact anything accidentally that would be detrimental to the operation of the rectifier or the output. But these are the passwords, so there is a user and a supervisor. Okay, so we want to check rectifier status. So we come in, walk into that room, you saw that display on the beginning, 130 whatever volts, charging 9 amps on the output, green LED on the corner, that's great. You hit any of those 3 buttons underneath there, this is going to be the screen that pops up. So this gives you the state of the rectifier, float charge, and then it's going to tell you, hey, here are your options. You want to monitor, config, or cause a command. Well, we want to monitor. We want to come in and we want to say, hey, let's just take a look and see what our system's doing. Let's see what the AC input voltage is. Well, I'll show you what you have the options to, but for right now, that's what we're going to want to take a look at. So, okay, we're in flow charge. We want to check monitoring. Hit the button under monitoring. Now, monitoring, it's going to give you want to see measurements. Okay, so under measurements, you want to view. Click view will give you the parameters, and we're going to go through them right now, of voltage and current and temperature, and a few other items relative to the operation of the rectifier, you click on View. At this stage of the screen, and we'll touch on this later, if you want to see an alarm or event history, you click on Next under Measurement. So this is the only thing that's not really super clear as far as you kind of have to know that you're going to click on View under Measurements to get real-time system information. You click Next under Measurements to get Alarm, either real-time or historical view under Measurements. So, but right now we want to take a look at real-time system activity. So we click under View. Now the slide that, or the graphics that I had from AEG, this is for a smaller rectifier where it's saying 24 volts, excuse me, it's a 28 volt because it's floating, but it's a 24 volt charger. For us, we have a nominal 125 volt charger, so it's going to say 130 or whatever it's going to be. But just so you know, that's that's why you see that output voltage as being low. For you, it's going to say 100, 30, whatever. And then amps. The load, again, a lot of your systems, the loads are driving, indicating lights, maybe some other monitoring within the station, usually a relatively low load, sometimes, I don't know, 5 to 10 amps is probably more common. The actual current that the system provides really comes from the battery when it's required to, throw breakers or trip, breakers and activate gear and so forth. So that is what you'll see under. So right now we're at the screen here showing the output, current, and voltage. Under here is our next button. We're going to click that red button under there again, and it'll give you next, and it's going to start, and you just scroll down. So we saw voltage and current. Then it'll tell you just the actual battery current. So the current before is sum of the load and the battery. So here's just battery current, charge and discharge. So should you happen to be deployed out there because of maybe you're investigating an alarm, you can take a look and see what is current is actually coming out of the battery and supporting the load. And again, typical charge current for a battery in a full state of charge, about an amp or so, maybe a little less depending on the size and number of strings. Here you can actually get your AC input voltage, temperature of the battery, as well as ambient temperature, ampere hour meter, the amount of reserve time calculated into the battery, and remaining charge time. That's if you walk into a system where you manually put into a high rate charge. It's going to time out. It's not going to allow you, the system's not going to allow either itself to put itself into a high rate charge for undefined amount of time, or it's not going to allow you to put it in high rate charge for undetermined amount of time. It's going to time out. Anywhere from 24 to 72 hours is usually the window that's factory sets based on the size of the charger, size of the battery. What the potential there is, or what they're protecting it from there, is somebody putting in a high rate charge, walking out the door, and then just having it cook the batteries for extended period of time until something fails. So that's why that's on a timer. And you can take a look and say, hey, I have 72 hours left on a 100-hour high rate charge. So anyway, that's what can be checked there. So so now we want to, okay, so again, you just kind of, you'll eventually exit out of that. You scroll to the bottom, you'll exit out of that. And now we want to view alarm history. So now we're back at the way that screen looked, just the way you walked into it. Had the voltage and current and green LED. You hit any of those 3 red buttons underneath, you're going to be able to get to this again. It's going to give you condition of the rectifier, going to give you the option to monitor config command. We want to monitor again, but this time instead of viewing real-time condition of the rectifier, we want to take a look at the either active alarms or alarm event history. So we click next, the red button under next, and one or two screens are going to pop up. If you're in an active alarm situation, it is going to list the number of active alarms, and then you're going to hit view, and then that's going to give you your first active alarm. So it's not uncommon for a rectifier to have multiple active alarms. So you lose AC input power, you'll have AC mains, low mains failure, rectifier failure, battery discharge. So all those things are kind of those are all conditions relative to the failure of the AC input. But they could be multiple alarms coming in at the same time. Likewise, in the event history, you'll notice when you start to scroll through that, if there are any events recorded, it's not uncommon that they're all time-stamped very, very, very closely. I think it pulls like every second or two to within each other. That it's not going to say, "Hey, this alarm came in at this time," and wow, this one and this one and this one. So it will give you a timestamp it with the date and time that the alarm came in. The way you work your way through that history is you click on View to get the history, and then it'll show you what the event was, and then it also timestamp it. I'll show you. That's actually the next screen that shows that. So once you finally took a look at all your different events and the different times that they logged in, you'll eventually get to the bottom of the list. And the way it lets you know you're at the bottom of the list, it'll say software version, and it'll let you know. Once you have that, once you see that, you hit the bottom, and then you can hit next, and it'll actually scroll you back to the top, and then you can just escape. You can just escape out of that. But again, that's just to let you know when you've hit the bottom of the history list. So when you are looking at an alarm, here we're taking a look at DC voltage alarm. If I hit next, then I hit this red button, it's just going to go on to the next alarm. So it'll tell me, okay, low DC voltage alarm, and maybe I was running on battery. There's probably an AC or a low mains alarm failure right around this time as well. So there could be other alarms, but again, you just keep hitting next. But if I want to see more about this low DC voltage alarm, I'm going to click underneath the View button, and then that's going to give me the date and time. Actually, I don't have the third screen or screenshot I'd like to have on here, but it'll alternate between the date and the time that alarm came in. So the screen will flash back and forth with when that alarm was pulled in. And then you just keep hitting next, and that'll scroll you all the way down to, hit next over here. That'll scroll you all the way down to the end of that list. You'll just take a look at all the alarm event history, and that'll, again, you'll see that, let me go back here. Till you get to that software screen, you finally see no more alarms, and then you're at the end. So the event or alarm, this is just what I was talking about. Click on View. That'll get you actually to the threshold that alarm is set for. Again, we're talking about a 24-volt system here, so it's a little different than our 125-volt system. But again, our systems are set for 120. So as soon as you hit 120, which is going to be almost instantaneous, it's going to say, hey, we're on battery, or we don't have charge current voltage available for the battery itself. You click next, it'll give you the date, and these are the two screens I meant that toggle back and forth. You actually click next. I said they toggle back and forth. You click next, and that'll take you to the time, and that's how you view the individual alarms. Clearing alarm history. This is, again, a command function that's going to require a password protection. It's going to be a user password, so you're going to be able to change something inside the rectifier, but you're not going to really, at least in this menu, change anything relative to the operation of the rectifier. That's really in the config menu. So monitoring, you're not going to be password or ask for anything. Command you're going to be, but you're only going to be able to clear history and maybe put it into a boost charge or take it out of a boost charge. But you're not going to be able to really change the language or do anything of that nature. That comes under config, and that's going to require supervisor password protection. And really, there's no reason for you to be in the configuration menu or mode of the rectifier unless something was not set properly from the factory or at startup. And even then, that would be someone probably from our company coming out to do that work. So again, what we want to do now is clear that alarm history. I'm going to go through this command function a little bit later, but because it does relate to alarms, I thought I would show you how to do that. So you just got done monitoring your alarm log. You want to clear it out. The alarms, any number of reasons you want to clear out the alarms. They're particularly old. I mean, they'll stay in there until they're eventually pushed out due to storage. The alarms could be related to maybe a faulty or a bad battery, and now you've replaced the battery. So you don't want people anybody coming after you to think that those historical alarms have anything to do with the battery that they're looking at right now, because it's a new system. A number of reasons you want to clear out the alarm. Click on command. So, and then once you get to the command, it's going to give you a number of options, and I'm going to show you what those are in a second, but keep hitting under next till you come up, clear history will come up. Okay, bingo, want to clear history? Hit enter. This is what I talked about, password protection. Now it's going to ask you for the password. Red buttons underneath correlate to increasing the number. And then once you hit the desired digit, click or hit the red button underneath the arrow to advance the character to the next position till you get it in. You hit enter, and then, hey, do you want to clear history? Yes, and then or not. If you're not, cancel. Just hit no, and it'll take you out of that screen. Command functions that you can do in addition to clearing the history. You can put into a high rate charge. Why would you want to manually put your rectifier into a high rate charge? Well, there's a couple of thoughts there. Sometimes you have 92 cells within a string. You can see a spread in voltages amongst the individual cells. The thought is you go ahead, you equalize, you can help level or even out the voltage across the strings, which does happen. But if you see a real significant spread across cell voltages within a string, usually that's an indication there's something else going on, and those voltages will eventually spread again. Another reason that people do it is after they've added deionized water or distilled water to the cells, topping them off, they'll use an equalization or a manual high rate charge to more or less shake up the electrolyte and the distilled water. These cells are relatively small. You don't really have to worry about stratification of water and the electrolyte. They'll eventually mix just fine on their own, but it's pretty common practice from what I've seen in a lot of other installations for people to equalize after adding water. If you have a brand new battery that you're putting in, you put it in manual commissioning charge. Like I said, that's actually a slightly higher, longer charge that goes into the battery, more actual current pumped in the battery for a longer period of time. And that's done usually on a brand new installation or when the batteries are replaced or changed out. And then again, you want to get it out of a high rate charge. You don't want to wait for it to time out. You can manually do that. Manually adjust voltage. No, you cannot do that right now. That's something we're going to be doing over the course of the next year, is updating the firmware across New York and Maine. For the AEG rectifiers, there was a option that wasn't spec'd on the original purchase of the batteries, but it's something that they want to have done now or have the ability to do now. So we're going to be coming in across the network and updating all the systems. So you will have that option to change the output voltage. Battery test function will actually put a momentary load on the battery. using the system load. So that's a test function, clear history, as I said, and you can even change the display. So again, not a lot of command functions that you're going to want to really have to do. Like I said, clearing alarms and equalize is probably the other. So I thought I'd just show you this again real quick, how to, again, pardon me, you're just below the highest level, screen, hit any of those three buttons. Okay, hey, what are we doing now? What's the status? Float charging. Monitor, again, do we want to look at real-time system operation? Do we want to look at alarm, either active or historical? Config, again, really want to stay away from that. There's really nothing much for us to do with that button, used for startup and factory settings. Command, okay, so we want to command just now, instead of clearing alarms, we want to set high rate charge. So we just keep hitting next, next, next. We'll eventually see set high rate charge as an option. Yes, we want to do that. Password protected. We get through that. Do you want to set high rate charge? Yes. You do that, you can really pretty much walk away from it. You don't have to, again, it'll time out. You don't have to stay there and or come back to the site to take it out of equalize or high rate charge. Configuration functions, like I said before, this is something does not really have to be done, but you should know it's an you have the ability. You can change passwords. Actually, not all the functions are in here because you can change language. You can change settings and protections and alarms. All factory set, nothing again, and they are going to require the administrative or supervisor level password protection. So again, you get prompted for that. You don't want to do it. You hit exit, you get out of it. Again, really no reason to even be on the configuration menu at all anyway. Communication options, this is to let you know the protocols that are available. I mentioned and again, we have some people in-house that are much more familiar with the protocols and Modbus and what else the other options are for remotely interfacing with the rectifier itself. I just wanted to put the slide up here to let you know that it's available, and only because, frankly, it's used in a lot of your systems across, in a lot of systems across your network. I apologize. Also, resolution here got a little diluted as I blew it up, but that gives you an idea what that card looks like. Maintenance, not a lot of maintenance to do to these rectifiers. Your environments are pretty good. Keep in mind these battery chargers or rectifiers are used across a myriad of applications: oil and gas, chemical refining, manufacturing. And those environments can get pretty dusty. Anyway, blowout here they recommend yearly. Certainly do it as needed. It would be my recommendation. This is somewhat ambiguous. Regular intervals, inspection, including disconnecting the main AC input to the line to the rectifier and the battery. That's nothing we typically see here in the States. Usually that recommendation would be, inspection and periodic retorquing of the connections. Here they're saying, mechanically, on an outage or something of that nature, physically take those off. Again, that's a recommendation for service from them. Checking for connections, checking for loose wires. That's just part of your visual. If you do have loose or bad connections, or a connection that is actually worn through, or a cable that is worn through to a chassis, something in that nature, it'll come up as a ground fault. You do have ground fault, depending where that is in the circuit. We do have ground fault detection on all your rectifiers. There are filters used on some of particularly the larger units, area inlet filters at the base of the front cover that you open up. Just take those out, blow them out, or they can be changed. And certainly checking the operation of the rectifier and voltage levels, that's just part of your normal routine on maintenance. Probably should be done on a quarterly or semi-annual, minimum and annual interval. Rectifier bridge fans, mentioned these are diodes. They have heat sinks. There are cooling fans on the larger rectifiers. They say they have about a 5-year service life. Those fans are temperature controlled, so your units typically are not running at full load. So usually you don't see high heat where you would have those fans running all the time. So that's something to keep in mind, though, that they do have a finite service life. Input switch, that's lower left-hand corner of the battery. That's the rectifier. That's your AC input. So you open that up, and that's going to have you running on batteries. The charger isolation switches, again, and these really come into more for battery maintenance or things as issues as they relate to rectifier service. So sequentially, if I want to shut a rectifier down for whatever reason, say you have parallel rectifiers, you have a tiebreaker, you put them together, you can actually take one out of service. The sequence would be open up the AC input breaker, open up the charger isolation, or I'll call it the battery isolation switch. At that point, your rectifier is totally down, and then you can open up your load isolation switch. Keeping in mind, the other side of those the other side of those disconnection switches are still live. I mean, you still have from your AC input, obviously the bottom side of that breaker, you have physically have to turn it off at the load center, and again, common sense stuff. But I just wanted to mention that. But that will, for all intents and purposes, kill the power within the rectifier itself, so you can work within the rectifier. Okay, and these are the two primary switches that we use, depending on, again, if we have parallel systems. Certainly to work on the battery, we're using this isolation switch S1. If we have the luxury of parallel systems, and even then, we're mindful or try to minimize anytime opening Q2, but Q2 is the load isolation. So again, once you open this, you lose rectifier output and battery output. These rectifiers are called battery eliminators, or known as battery eliminators, meaning that they can run with or without the battery in service. There are some rectifiers out there that require a battery to be tied into the system for the rectifier to run. In this instance, these rectifiers will run without batteries. Will supply regulated load without batteries. Alarm event, troubleshooting for alarm or events. Not really a lot going on here other than to say charger fault. There's an F1 fuse, and I've only seen it actually blown on installation, inadvertently or accidentally blown on installation. But there is a F1 fuse, and it's clearly marked. It's on the lower left-hand side of the cabinet, and there again, everything is clearly displayed. The manual itself is inside the rectifier, but I just wanted to give you an idea, an overview of what troubleshooting is probably going to be on these rectifiers. And really, for the most part, it's going to be an AC input power issue, or it's going to be an issue related to, well, I'm going to show you right now what the other potential issue that we've seen in the past has been related to the electrolyte sensors. They are sensors, and this one, you really can't see it, but they are little sensors mounted to the side. We really should have that drawer slid out, but the sensors are mounted to the side of the pilot battery cell, and it's looking for electrolyte level. You can't, again, these drawers pull out, and these cells are installed in such a way that you actually can't see the electrolyte level on the batteries. Now here the cells are somewhat opaque, so we have a pretty good lighting in this particular room, so we can see the level. And this is actually a problem. This is an issue where the electrolyte was allowed to get too low. The plates became exposed. As the plates became exposed, the cells themselves start to heat up. They get hotter. They off gas more, driving the electrolyte even lower, exposing more plate. It's called a thermal condition, or you may even have heard the term thermal runaway. But back to these sensors. So these sensors are notorious for falling off of the side of the jar, and there's a very particular way that they need to be reinstalled. So a lot of people just try to tape them from the back onto the jar. The alarm stays active. They get frustrated. They just kind of coil the sensor up, lay it in the bottom of the cabinet, and put a tag on the outside. Hey, phantom alarm, we know there's an alarm going on here on the system. You walk into the room, that red or amber LED is lit. It's lit all the time. So if you have like a general summary alarm on the system, you don't know to really look for it. It's like, oh yeah, that thing's always an alarm. It's not a problem. It's, that's because of the sensor. We strongly recommend installing those sensors. For one reason, it'll help you get away from situations like this. Whereas the electrolyte level got to the point that the battery's heated up to a temperature of almost 150 degrees, and actually ruin the batteries. So when mounting the sensor, 3M makes a clear two-sided tape. It's important that there's a bond between the sensor itself and the jar. So you can't just tie the sensor to the jar, or even tape it from, like the big piece of duct tape over the back of it to smash it onto the battery. We need interface between the sensor, the tape, and then the jar. So that's clear two-sided tape. There's a bullseye, or what I'll call a crosshair. One side of the sensor, the other side is blank. It's the bullseye side of the sensor that actually mates to the cell, and you just put that right in the middle between the high and low fill line on a pilot cell, and that should clear your sensor alarm and allow you to monitor all real-time active alarms easily. Like I said, it is something that AEG is aware of, and they're working on trying to come up with a system that's a little more reliable for those sensors. Maintenance, PPE, you know what you're doing there. Here, this is actually a generic slide, but saying about soda ash or bicarbonate soda for lead acid batteries. Boric acid solution for NiCad batteries is a recommended practice for cleaning up spills. Protective apron, resistant gloves, goggles, face shields, certainly working around the electric side of the rectifier, insulated glove, 1,000-volt insulated tools, which again, your company should have protocols in place for the PPE required to be working on battery systems and DC rectifiers. NERC guidelines. So there's not a lot NERC has related to maintenance of the rectifiers themselves, though they do speak to the battery quite a bit, and that's because the battery is deemed as the weakest link, and I guess they're probably not wrong in that conclusion. So what we're looking at here on the quarterly inspections, they want you station DC voltage, electrolyte levels, unintentional grounds. As I mentioned before, the rectifiers do have ground fault indication, so they're going to it's going to alarm if there should be a ground fault. Every year and a half, they want you to verify float voltage of the charger itself, battery continuity, terminal connection resistance. That's the straps, if you can get to those. That can be done with a digital low resistance ohm meter or an Albert test set. The battery intercell, again, those are the metal connections that go in between the positive to the positive to negative within the string. They want you to verify the integrity of those, and then inspect cells for any sign of damage, physical damage, leaking, things of that nature. So one of the benefits, and there are several benefits to NiCad batteries, they're very robust, resilient battery, been around for a very long time. I mentioned Utilities are very cautious as to what technologies they'll adopt going forward. NiCad batteries are very among battery chemistries. They're among the older of the chemistries, and they have proven themselves to be reliable, such that they recommend, they being NERC, load testing the batteries, or at least measuring the performance of the battery. And there's really the only best way to do that is with a resistive load bank load test of the battery every 6 years. So other battery technologies are every 3 to 5. NiCads allow you every 6. And this is what a load test looks like. Our monitoring system is the snapshot to the far right-hand side. Because these tests typically are, I mean, they usually run 3, 5, or even, we've seen them 8 hours. But because you're running, a test on 92 cells, to manually run through and try to take those, and we've seen people do it or try to do it anyway, run through with a voltmeter. By the time you get down to jar number 92, it's time to get up to the top and start over again. So you're not really capturing real time where the individual cells are or how they're performing against the clock, as it were. So maintenance, why do it? So trending, we're trying to get ahead of any, predictive maintenance is what we're looking for here, trying to get a hold of the idea of when to replace a battery, maintain or at least help maintain reliability and integrity of the DC system. Warranty requirements of battery manufacturers require some kind of documentation, and that's important too, not just why do the maintenance, but retain the documentation as well. Battery warranty, and then also NERC. They'll come in, they'll do audits. They want to see that you've been doing indeed what utilities have agreed to do as it relates to maintenance on DC power systems. Here's just one thing I'll show you. We talked about a little bit earlier, continuity or resistance between cables. This particular cable was just lightly pulled on and just pulled right out of the lug. It was a bad connection. That would have been caught if there had been a resistance check at the base of this post here and the base of the next post that the cell was connected to. That would have come up as an extremely high reading relative to the other cables within the system. Again, that was never done, and we knew that just by a slight tug on that cable, yanked it right out of it. This is also something else that Avangrid is and NERC is big on monitoring, and that's the most positive post of the battery string itself and the most negative post of the string itself, and the cables going over to the load or to the rectifier. Again, you remember these are all kind of mechanically tied further down the line at the same point. So this lug here is tied to both the rectifier and the load, but you want to make sure that you have a good mating surface from jar number 1 and your cable and jar number 92 and your cable going out. So to do that, you actually need to measure the resistance between that lug and that post. And that's the presentation, my name and contact information, as well as technical support out of Spain. Pedro Sanchez is a phenomenal guy, speaks pretty good English. He's forgotten more about these units than I know. He's good on the communication side as well. So as far as the interface, I'd mentioned earlier the different protocols for remote monitoring other than just normal, dry contacts on the system. He's a phenomenal guy and a tremendous resource. Keep in mind that his time is Madrid time. Okay, any questions or issues? You have my contact information there. Thank you if you actually took the time to sit through this presentation online. Thank you very much.